We're here at the Knights Racing Baja SAE shop. SAE stands for Society of Automotive Engineers. Here we build a single-seater off-road racing vehicle designed, built, and tested by UCF students. Today we're going to talk about our senior design project, the Shock Dyno. Our Shock Dyno is built to test compression and rebound forces in the shocks used by the race vehicle behind me here.
This was a 9-month project that we started back in September 2025 and has taken us all the way to May 2026. And in those 9 months we have gone through the entire engineering process from brainstorming to design, and now we're in the final stages of manufacturing. In that process we came up with over 40 system requirements that's going to really help us meet those Baja customer needs, and now we're in the final stages of manufacturing the system and delivering it to our customer, the Baja team.
Myself and my team have been designing and building a shock dyno for the past 2 semesters for the SAE Baja race team. Today we're finishing up programming our linear potentiometer and our load cell, and hopefully by the end of today it'll be ready for the SAE Baja team so that they can use it here in the shop.
My role in this project was the instrumentation. So basically I worked on procurement on the load cell, the linear potentiometer, basically all the things that really make the shock dyno intelligent. So we need a way to capture force, we need a way to capture displacement and velocity. Those are one of the main things the stakeholders highlighted they needed in order to properly tune their shocks. So I had to do a lot of research. A lot of this instrumentation, data acquisition stuff, it's really out of our mechanical engineering syllabus. Luckily, we just tested our system and our linear potentiometer worked perfectly yesterday. We just tested our load cell and we're getting really good readings, so really excited about how it's all coming together. So here's our shock dyno fully put together. As you can see, the core mechanism is a simple crank mechanism. So with each spin of the motor, it reciprocates and it's able to test the shock really nicely. We chose this mechanism over other things like a Scotch yoke simply because of manufacturability and how well the line of force is transmitted through the axis of the shock. As for the instrumentation, we have a linear potentiometer on parallel to the axis of the shock and a load cell right above it. Powering all of these sensors is our little electronics board here. Our NI USB DAC, this is what's taking the information from our linear potentiometer and load cell and outputting that onto our software. And this brick right here is our amplifier for our load cell. Without this, our computer can't pick up signals from the load cell because it outputs really small values in the order of millivolts. So this amplifies that signal and is able to be read by our computer. So as you can see, with each compression and retraction of the shock, it's outputted on the graph really nicely, almost with zero latency. This is the underlying block diagram for our graph here. Now I won't go too much into detail, but basically it's what kind of wires everything up. It uses the output from the data acquisition device where our force gauge and linear potentiometer are hooked up to, and it uses the voltage readings and it normalizes them into actual real-world values such as displacement and newtons.
So all of these parts on this Shock Dyno are designed to be either laser cut or cut in our machine shop here on campus using a 3-axis mill or a standard lathe.
As for the design of our shock dyno, we chose to go with a crank-based mechanism. We were faced with several budget issues but still had to meet the needs of Baja. This design is essentially the skin and bones of what a shock dyno is meant to be, where we can keep it cost-effective and simple while still meeting all of our engineering requirements. Installed on the sides, we have 2 uprights that are engineered to meet the dynamic loads of what a shock dyno faces. Installed all around on our shock dyno are the individual sensors that we need to help us extract the information to create accurate shock characteristics.
We had to do some quick engineering, some reverse engineering of the previous shock dynos and how they converted the signal, an analog to a digital signal. This was the old electronic / DAC system of the previous shock dyno. Again, more reverse engineering. We took apart the plate and we decided that we could reuse it.
Throughout this project, we faced multiple limitations, including our budget, the space the Baja team had in their shop, and the power they were able to supply our dyno. At the end of this project, we now feel confident that we have met all of the desired requirements and have overcome all of the limitations. Over the course of this project, we learned a lot of valuable skills, most important of which is how to be an effective teammate. To conclude this project, we wanted to give a special thanks to our advisor Rich and our professor Kurt, as well as the SAE Baja race team and the UCF MAE department. Thank you.